All right, so in this video, we're going to talk about the synthesis of alcohols. So I want to start a bit about talking about reduction and oxidation reactions, because synthesis of alcohols tend to be, or in this video, we're going to talk about reduction reactions in terms of synthesis of alcohols. But to start with, when a molecule is oxidized, that means its oxidation state increases. Usually this means also you're adding oxygens, so you'll have reagents that are usually pretty oxygen rich. So things like PCC or chromium oxide or peroxides, things like that, they just have lots of oxygens. On the other hand, reduction reagents decrease the oxidation state, meaning usually are decreasing the amount of oxygens. So you usually have molecules, your reagents are high in hydrogen. So just to get a perspective with like our carbon molecules, CO2 or carbon dioxide has an oxidation state of 4, just because we have 4 bonds, and then all of the electrons are going into these oxygens. So we have 0 going into carbon, which is why it's 4 minus 0. Over here with this carbon with the 4 hydrogens, we have 4 bonds, but then all 8 electrons are being pushed into this carbon, which is why we have a -4 oxidation state. So typically, if you're in the middle here, you can either reduce or oxidize your reagent. We're going to go down to talking specifically about aldehydes and ketones, getting synthesizing alcohols from aldehydes and ketones. Sorry. So to begin with our aldehydes, so the oxidation state of an aldehyde is +1. So we're talking about this carbon in the center here. So of course we have 1, 2, 3, 4 bonds, and then 1, 2 electrons from this hydrogen being pushed into the carbon, 1 from this carbon, and then of course 0 here. So this is where we get the +1, 4 minus 3. And then when we get to an alcohol from here, our oxidation state is actually -1. Because for here we have 1, 2, 3, 4 bonds, of course, 2, 4 from the hydrogens, 1 from the carbon, that's 5, 0 from the oxygen, which is why we have a -1. So we're reducing, of course, that's that reduction going from a more positive number, as we were looking here, to more negative. And then again, the same thing happens with ketones. Ketones are just a little bit more oxidized to begin with, +2, and then you go down to that -1. So this is kind of where we're going to start. We are going to be looking at reduction reactions to synthesize those alcohols. And this is why we're lowering the oxidation state. So we can predict that our reagents are going to be full of hydrogens. So let's look at a couple reactions here. Let me, sorry, zoom out a little bit here. Okay, we are. I think, here we are. Sorry about that, guys. So here are some of them. You can just see just by looking over them quickly, like here reagent, sodium borohydride, 4 hydrogens here. Here, this is just deuterium, which is an isotope of hydrogen, but again, 4 of them. Lithium, aluminum hydride, again, 4 hydrogens. In our nickel reaction 2, we have 2 hydrogens. So again, we're going to have lots of hydrogens. There are no oxygens anywhere here, as you can see. That would be reserved for our oxidation reactions, but for this we are doing reduction. So let's start with the sodium borohydride. We do have an aldehyde here. We add sodium borohydride, this methyl oxide group, and then some water, of course, for a workup. And we do end up getting actually the secondary alcohol. Oh no, that's primary. I'm sorry, that's primary alcohol. This primary alcohol, I just wrote that kind of weird. And then the same thing happens with the sodium borodeuterium, except for we do have this deuterium here instead of the hydrogen. And then again here, the only difference here is the deuterium oxide. Our lithium aldehyde does that as well. So let's look, actually, I guess we could talk first about our reagents. So this sodium is a mild reagent, versus this lithium over here is a strong reagent. Usually do it in cold conditions so that it doesn't explode or react really violently. And then that sodium borohydride can be done more in like room temperature, heated conditions, just because it is a bit more mild. Our hydrogens here do act as our nucleophiles for nucleophilic attack. We'll see that in the mechanism in a moment. And then down here, our nickel reaction. This is actually just like the start of one, but these are Randy nickel reactions. They are very, very active. Sorry, this is not super nice. I don't know why that's doing that. Oh, here we go. Now we can see it. So this nickel, this one's actually super reactive. It ends up causing fires. Like it catches on fire very easily. Another thing to note about this one is it does actually react with both alkenes and carbonyls versus this lithium and sodium borohydride are only carbonyls. So you can see it has actually reduced this carbonyl and this alkene and this carbonyl into an alkane and an alcohol. Let's look at the mechanism just a bit now, so we have an idea of what we are talking about. Sorry, let's move this back down. It's kind of in our way here. Okay, so we have our aldehyde, and our borohydride here. Of course, remember that our hydrogen is our nucleophile, so it is going to attack that carbon. It's positively charged at this point, remember, because of our oxygen. This is where our methyl oxide comes in. There's like a small hydrogen bonding here. Doesn't last very long though, as this gets pushed up. So then we come over here. We've gotten rid of this double bond, now have a negative charge here. We have another hydrogen here. So now our oxygen is good for a nucleophile to attack this hydrogen. We are attached to this oxygen now, so we have this borohydride molecule on our alkane or aldehyde. And before we get into this, let me go back. I did forget to mention there are 4 equivalents of this for every 1 sodium borohydride because there's 4 hydrogens. So each hydrogen is going to attack one of these molecules, and you're going to get something like this. So this big massive molecule with this boron in the center, your oxygens, and then whatever your R group is here, it happens to be that cyclohexane. But you're going to get this huge molecule like this. So this, I kind of did it like this, so I didn't have to draw 3, but there will be 3 of these all kind of attached in this manner. And then for our workup, we will have water or some sort of acid, sometimes of H3O plus or H2SO4. Doesn't really matter. We just need a hydrogen. Depends on the reaction, I suppose. It does matter. But this will hydrate that oxygen, giving us an alcohol. So again, this is a reduction because we went from an aldehyde or a ketone to an alcohol. You can see here's that hydrogen that we added. And we actually got rid of, in theory, one of those alcohols because we did get rid of one of those bonds. So we went from a double bond to a single bond, and we added a hydrogen, which you add a hydrogen when you get rid of that double bond. So that makes sense. But again, that is your reduction reaction. So we'll come back here, but in order to, a couple ways to synthesize alcohols, we start with an alkene or an aldehyde, and then we add a reduction reagent. This could be a sodium borohydride. This could be sodium deuterium, lithium, aluminum hydride, or even our nickel Randy reaction or Randy nickel reaction. I think I said that correctly. Let me make sure. Yes, our Randy nickel reaction, which depending on what you want to do, what you want to reduce, you can choose your reagent appropriately, also with the conditions, because again, like this borohydride is a very mild reagent, lithium is stronger, nickel is our strongest, so like results in fires. But yeah, so this is a couple ways you can synthesize alcohols from aldehydes or ketones. So All right, so back to our synthesis of alcohols. In addition to those reduction reactions we're talking about, we could go back a little bit to previous units where we also use ketones and aldehydes to synthesize alcohols. One example here, of course, are Grignard reactions. So from an aldehyde, and if we add an aldehyde with a Grignard reaction or Grignard reagent, we get a secondary alcohol. And then if we did this with the ketones, if this was an RN7H with a Grignard reagent, we would get a tertiary alcohol. So we'd have one more R group here. So that's another way. Our Grignard reactions are also always a great way to get alcohols. They never fail you. Sorry. And then there's one other way, we did talk about this earlier, but and with oxygen are hemiacetals. If you add water or some sort of acid to a ketone, and usually a ketone in this instance works best. Usually get a hydrate. So actually get two alcohols. These kind of split here. We've looked at the mechanisms before. We won't do that again, but that is another option. And then if you could do an ester and an alcohol, so it's hemiacetal with an OH group, actually an alcohol group and a ketone, and then of course our acidic workup. But again, a couple other options for creating alcohols. This is really pretty important in chemistry. So there are a lot of different ways that we have figured out how to do this. So those are a couple ways that we can synthesize alcohols.